Yeah, thank you everybody for turning up. This is the third session of the second part of the forensics course, hosted by Klaus. So I will happily hand over, and I hope you all enjoy this session. Thank you.
Yeah, thank you very much, Carl, and welcome from my side. So today's topic is one more session about memory analysis. This time we'll be dealing a bit more about malicious code. So what I'm talking about when I'm talking about malicious code is mostly rootkits, user mode and kernel mode, and how to extract malware from the memory samples so that we can reverse engineer it or scan it with antivirus scanners or whatever else we want to do with it, search for IP addresses of command and control servers, etc. One very short topic right beforehand is creating timelines with volatility. So that's our first topic. So there are lots of timestamps in memory dumps, like process creation times, sometimes process termination times, thread creation times, the compile times of code like driver modules, DLLs, programs, network socket creation times, lots of timestamps in the registry. Eventually, we have log files, mostly Windows event log, that have timestamps in it. And volatility 2 and 3 come with a timeliner plugin that allows us to extract these things and to import it into a later another tool for timeline visualization or analysis, like, for example, our autopsy. There's something wrong. -H. Oh, should have worked. Yes. This is a help message. So we can narrow down the type of events we want to import through the -- type option. So if we omit this, it will just import everything. And we can also have the usual way of tailoring our output into something we'd like to have. So, and if we do that, for example, when we try this with a Zeus image like this one, we can give it the timeliner, and it's very, very recommended that you direct the output to a file, because this will first take a long time if you do this on a machine with a large amount of memory. And if you have to do this again because you may have missed something, this eats up a lot of time. So especially with the plugins that generate a lot of output, you should direct this into a text file or into your JSON or whatever file and have this here. So I'm not actually going to execute this, just showing you the timeline, which is the result here. So, and as you can see, it's mostly just a thing with the timestamp here. Then we have the type of the event and the actual data of the event here. So it's by default separated by the vertical bar, but there are different things. So that's all they have. And as you can see, even these relatively simple memory image from very old Windows XP memory image has something like over 3,000 lines of output. So remember, when you have a big busy machine, which is really on a production level networks, this may go up into a couple of 100,000 of lines. So this is probably something you should really keep down into a text file. So autopsy, for example, comes with a plugin that allows you to import this output from volatility into their own timeline analysis tools. So much for timeline creation. Now let's talk about rootkits. What is a rootkit? I think you're all familiar with the concept. For those of you who are not, a very short introduction here. It's a software or several pieces of software that hides the presence and the activities of an adversary or an intruder on your systems. So it means it hides processes. The attacker doesn't want us to see files, directories, network connections. It may even lie about free disk space if they use this to, for example, extract data. They have to store that data perhaps on that machine as a step in between, and this may eat up quite a bit of disk space. So they may be lying about free disk space, or if they use it as a virus server or something, that happens sometimes. Also, if they install sniffer, the rootkit may lie about which interfaces are in promiscuous mode, so that we don't can see the activity of a sniffer in an easy way. So these rootkits typically come into two flavors, user mode or kernel mode. In user mode, all manipulations the rootkit does with the operating systems are done in user space. So the kernel is basically untouched. So what can the attacker do? He can replace system programs like PS, LS, dir, whatever. Or they manipulate the system libraries like the Linux libc or Unix libc or the kernel 32.dll on Windows systems. So the downside of that is when they really write into disk, it is easy to find with the persistent storage analysis tool. So that's what Toby will be talking about next week and the week beneath next week. Another technique popular on Windows is to inject code into every process on the operating system. This can be done through calls from the Windows API, which usually means we take a library, a DLL, map this into the address space of the process, and then execute another thread which executes code from that library. So as I said, it doesn't manipulate the kernel data, but to do so, especially for every process or to write to a system program, it means you need root or admin privileges to do so. So you have to use as an adversary a kind of exploit before that either directly gives you network access as root or use some local privilege escalation exploit. So all user mode rootkits can usually be detected in the very old way from the 90s. We take a clean media like a CD or even a read-only USB stick and have our uninfected tools and libraries with it and get a view of the operating system. So unless we have some preloading systems, this will usually work fine. We can even get around this when we statically link our tools. But memory analysis makes this task a bit easier. So what do we mean when we manipulate system libraries? The rootkit functions are located in a shared library or an executable, and this is mapped into the infected process on Windows. And this may then override functions from the OS or the pointers to these functions in a separate thread. So the thread is doing the overriding and redirecting the code to the rootkit code. On Unix suite operating systems, this is done a bit differently. It basically uses the LD preload mechanism, which means we can load a library before the libraries from the operating systems like the libc are searched. So in that library will then contain the rootkit code. You can do this for a single process through the LD preload library environment variable, but in a general way, you can put an entry into etc LDSO preload or etc LDSO conf directory. So another way would be to manipulate the LDSO code directly, the dynamic linker. So, and as I said, the malicious functions are then found before the regular functions, and the dynamic linker links against these functions before it finds the functions from the regular libraries. So when we search for these kinds of libraries, where do we look, or what do we look for? So this has been taken from the Malware Analyst's cookbook, which is which is a very nice book, even if it's a few years old. But I can very much recommend it. There's a lot of practical tips when doing forensic analysis. So if one of the things may be that we have a shared library or a DLL with a suspicious name, or a name that we haven't seen in our OS before. So then we may also have the kind of shared library with a common name, but it's loaded from a non-standard directory. Like we see something like here, Windows sys, correctly would be system 32, where the kernel 32 library is loaded from. So then we may see shared libraries that allow access to protected resources or to system security functions in processes that usually don't have anything to do with protected resources or system security. Or in general, anything that may be just out of context. They maybe not be malicious, but they don't belong into the executable normally, like a network or security library in a program without such functionality. So, and then let's see something with a more modern type of rootkit, which is the Bedevil rootkit, which is fairly recent here. You can get this from GitHub. So if you want to play around this on your own Linux system, please use a test system for that. You can work with this code. It has a quite long list of what it all does hide. So we can basically hide almost everything. It can install backdoors that depend on the environment variables or on the source port of the that you're coming from when you do a TCP connection or an SSH connection to the system. As you can see, it's quite extensively documented. I'm not going through all of this. Just showing you when you've compiled this, it's very easy to see here. You do this, it gives you a finger, but this is normal behavior for that rootkit. So don't be afraid here. And so it tells you what it did. It patched the dynamic linker. It put up an ICMP backdoor. It has a special username that you can give to the PAM backdoors. And if your TCP connection comes from port 25606, it will directly give you a root shell, and it will hide every other connection that comes from a port range between 39.389 and 41.172. And finally, if you use this environment variable, it can do the uninstall, which gives you another finger and usually throws you out of the system. So, and I've done a bit of a search before, so let's go to a forensic system and let's see what we have here. So the typical plugin to use for this is to use the Linux library list or similar plugins on other operating systems. and do a search of the all the libraries that are to be loaded into the different processes on the system. This is, again, taking some time. So it shows you the name of the task, the process ID number, and the address where it has been loaded, and the typical path where the loaded library has been located. As you can see, there's a dboss daemon, there's a VMware tools daemon. So this looks all pretty standard. As you can see, that library list can be a very, very long one. And here you can see that there are the first signs that there may be something fishy, because this looks strange here on systemd. Can't tell you why this looks so garbled, but in any way. The interesting thing is a bit beneath here. We see something like not lib64 or user lib64, but we see something from lib, which is strange because that's a 64-bit system, and so they shouldn't be sharing anything directly from that directory. Then there is something called libappamorg, so and so, and yes, that's a bit strange. So let's see if there's more AppArmor stuff in our listing. And so we can see, okay, it has been injected into quite a few processes. Okay, so as we can see, this is already looking a bit fishy. So we might give that library a closer look. And as we can see, this depends a bit. So on Windows, the plugin is called DLL-list, and on Mac OS, we have another plugin which is called Mac LDR modules. So in the end, that wasn't a very clever way of hiding, but I've left the code from the Bedevil rootkit unchanged. So in real life, this may look different when you're infected with Bedevil, because the intruders will change the names and the variables before they compile their rootkit. So here it's again on the slide. So that's mostly how you can find this, or you can do this with the persistent storage analysis. So let's go on and take a look at kernel mode rootkits. So what they do is basically the same thing as the user space rootkits. So they hide activities, files, network connection, and so on. But now some or all of the code is executed in kernel space. So that means not the tools are returning bogus data. The system calls at that level already do that. So, and whatever tools we use, even if we have clean tools from a clean media and link them statically, they still have to use the system calls from the running kernel. So we have no way of finding them on a live system. So we can, of course, turn the system off, but then we can't do any live analysis anymore. So, and so what we do is we take the memory image, and we can then offline analyze that memory image, so we don't have to rely on the bogus system calls. So, and instead we examine the in-memory data structures directly. There are many ways today how kernel rootkits work, but historically there are two common approaches. One of them is manipulating the call chain of the system call, which goes through the system call and or the interrupt table. The other way is, or adjunct is, loading a malicious kernel module or kernel driver. So we will have a look at both of these in a moment. So for those of you who are not familiar what interrupts are basically hardware interrupts, like when your mouse moves or you strike a key on the keyboard, or your disk finishing a read or write operation, or your network card has something to do and returns. So, and each of these times an interrupt is called, and there's a table with function pointers to specific interrupt routines that gets called when each of these interrupts or events from the hardware arrives. And there's also a special kind of interrupt, which is called a soft interrupt, which is used to call the various functions from the kernel. And this interrupt usually calls another routine here, which is called the soft interrupt handler. And this again calls another table, which is called the syscall table on Linux or Unix. And on Windows, it's called the service descriptor table, SSDT, or system service descriptor table. And but they both work very similarly. So, and again, this has mostly an entry for every system call on the system, like, for example, the Linux this get directory entries. And these will then in turn call the virtual file system and the actual file system and so on, until we are reading the directory from disk. So what rootkits do is they manipulate this lookup process. So if we hide very, very far down this chain, we can directly manipulate the system call code. So that leaves all these data structures unchanged. And the rootkit call code is actually inserted into the actual syscall function. This means usually we have a sort of jump instruction right after the entry here, which then executes in the rootkit and which does then jump back into the actual call. It's kind of an inline wrapper around the lower level functions. So then we can replace the entry in the syscall table with a pointer to a function of the rootkit, which is basically just another function in a different place in memory. And this is usually what gives these pointers away, as it points into a different memory region. And we can see this when we compare this pointer to the others in the system call table. So it then calls a rootkit call, which usually calls the actual former syscall code, because it still has to do some work, and it's easier to do this through the operating system routines than to program everything yourself as an adversary. So the interrupt table and handler and the soft interrupt handler are left untouched, and the base address of the system call table is also unchanged. So then we can modify the soft interrupt table, interrupt handler. So we just override it with some different code. And this then uses its own modified system call descriptor table. And the entries in the original table are, of course, unchanged, and they look nice. And even the modified table may look homogeneous. So they all point to some sort of rootkit code. So we don't see any pointers standing out here. But we still may see that the system call handler, the soft interrupt handler, has been modified, of course, because it's still at the place of the original pointer. So we have to inspect this code block to see if it's different from the original code. Or we may even find the modified system call descriptor table and system service descriptor table and compare it to the original one. So then we can do the same thing as we did before with the system call with the soft interrupt handler. We just replace it by a different entry in the interrupt descriptor table. So we don't have to manipulate the code in place there. Again, that pointer will stand out as it usually points into a different memory region. And the system service descriptor table in this case is left unchanged. So it all looks very fine here. And even the original pointer looks, when we follow that, we still have the original code in place and it looks all fine. But the manipulated or the replaced soft interrupt handler calls rootkit code directly, and it doesn't go through the system call table. So we have a couple of plugins to inspect these tables, which are called the IDT and the SSDT. So aptly, the Windows plugins are named appropriately. We still have an IDT inspection plugin for volatility 3, so may come in the future. Linux also has not only a IDT plugin for Intel architecture, it has also something called the check exception event table, which is just the name the ARM processor architecture uses for the interrupt table. And we have syscall inspection programs also for ARM, and some more plugins on volatility 3. And Mac OS is aptly named very similar. So again, when we start looking here, some critical functions like page faults or other things should always be handled by core OS functions or standard modules delivered by the operating system vendor. So kernel modules or some antivirus systems or other code may override certain system calls. So it's not unusual that there are genuine manipulations of these tables. So we have to have a clear idea what a clean system looks like. So we should have some memory images of a clean OS right after we've installed all production level software on it for comparison. Also as a word of advice, these are fairly old techniques. Attackers have since then found a lot of more function pointer tables in the OS and ways to manipulate them to hide their activities. And there are more volatility plugins to find them, but for time reasons and for a bit of a time constraints and explaining all these tables, I have to skip this here. But I think if you've gotten the idea around these tables, you will have no problem in grasping the concepts behind the other plugins. So let's talk a bit about kernel modules and rootkits. As I've said, modules or drivers are a way of adding functionality to the kernel or modifying functionality of the kernel. And so rootkit developers have found this a very convenient way to bundle their software and install it into the kernel. And it is easier than directly overwriting kernel data structures and injecting code. We can just use the standard module installation or module loading processes of the operating system. Sometimes there is a user space process to communicate with the kernel parts, so the kernel module. So we may find not the module directly, but also the socket or handle between the user space process and the kernel module, or the user space process directly. Sometimes it's not hidden. So the plugins are usually named after the commands that are used to list kernel modules. So on Linux, it's named lsmod, and on Mac OS 2. Windows has a whole bunch of plugins for that. Modules is the module list. Modscan also looks for unloaded modules which are still present in memory through carving techniques. It can also look for drivers and some more modules here. So, but let's start with a very simple one. Let's go into the live system here again. Pi minus f image. Start with the Lackner rootkits, and let's see what we get here. So I will shorten this a bit. I know this is LANman drive.sys. As you can see here, it is correctly installed into Windows and System 32. So the drive itself doesn't look problematic, but as we can see, it seems to be loaded relatively late into the process, as it's very far down the list. When you do this on Linux, the sequence of module loading is reversed, so the latest module is very far up on the list. So it's a bit different here. So we can see here, even the memory region doesn't look that problematic. So all we have to know is that the LANman drive sys here looks a bit fishy, because we know that, perhaps know that the LANman driver is typically called lanman.drv. So now that we found the malware on the system, be it a library in a user space process or a kernel module, how can we extract this? So one very nice tool for this is the Malfund Plugin, which goes through every virtual address descriptor block in Windows. And the virtual address descriptor blocks are just descriptor structures for every memory region that is mapped into a Windows process. And this plugin then searches the VAD blocks for code that may have been injected by malware. And one typical mistake from older malware is that they included the executable as a whole, which was allowed by the process. And that means they will get the MZ header into the block. And let's see if we can find this here. I do this with the Zeus image, which isn't too bad, because it recently has returned as the zload rootkit, of course, with a lot of updated code. And yes, you can see it here. It tells me which plugin I have, and the very first one I see has this MZ header here. I can also see there's some very suspicious looking code here, lots of empty instructions. Just this is more a standard library. So as you can see, it looks quite a bit differently. We get a bit of a disassembly from the very first part of this. So if we want to directly dump everything, we can use this with the -d function and give it something like dumpdir. This will, without a process ID, dump everything that's Malfund think is suspicious. So if we look into dumpdir, we can see a lot of processes, and when we see something like this here, we can take one of these executables, like, for example, the one from, let's see if, just the very first one. Let's see if we can do something like this. We can take a SHA-1 sum of this executable and then use our, for example, our browser and go to virus total with it. Got the wrong checksum here, but doesn't matter. And as we can see here, we have a Z-bot. So that's a very, very simple way. It also avoids putting up memory samples which may contain sensitive data or personal data. So we just take a checksum of an executable and see if the virus vendors already know about this, or sorry, the antivirus vendors. So we could also use this, for example, to put this into a reverse engineering tool like Radar or Ghidra or IDA Pro and see if it's really malicious. So then we have another way of doing this. We can use, for example, the mod dump facility to dump a kernel module. Again, this is quite similar, but we have to use the base address. Sorry. Let me see. There we have the right one. So I'm sorry, that was the wrong example. This one's here. So we can see here it dumps our part. And again, we can use the sequence of SHA-1 sums and go with it to virus total and see what we have here. And again, this is called fishy. So this is very simple. We just have to get this address from the modules list. So I can probably show you that before. Scroll a bit up here. Oh, no, don't have this here. Because for the plugin, shouldn't use that. So that's live. So we can see when we have the alarm drive here, we need this base address as an input for the -b option on the dump here. Here we have it. Okay. So, and if we don't use a specific option, of course, all the modules will be dumped. So this is probably not what we want. So, and lastly, we can do this with the proc dump to dump memory from a process. I think you already gotten the routine. So again, with the Lagma rootkit, proc dump -p1180 -d, just dump it here. Oh, I can see if it's an executable. Oh, really? A file tells me it's an executable. So again, SHA-1 sum of my executable. upload it to VirusTotal. Come on. And we have what we're looking for. So this is really a very simple way of dumping malware and have it then for analysis. Of course, on real-life production systems and real cases, we may have to take several samples, and this will usually take quite a bit longer than what I've shown you here. But sometimes we're just lucky and get a direct hit with VirusTotal or anything else. So, and I'm already nearing the end of my presentation. 45 minutes, just a very short span of time. So, as I've told you, we've seen only the very, very beginning of what volatility can do, and there are lots of more plugins and ways of doing things. So what I very much recommend is to read the documentation, of course. There are two very nice books. One of them I've already mentioned, which is the Malware Analyst's Cookbook. And the other book is also very nice. It's The Art of Memory Forensics, which is written by the volatility authors. I also recommend reading the volatility blog posts. They have lots of case studies and also quite a few things about community plugins. They have an annual contest for writing new plugins. So that's a very, very nice source of information. And then, yeah, practice makes perfect. There's quite a few memory samples around this. As you've seen, I've used the ones from the Malware Analyst's Cookbook, which is freely downloadable from the internet. Or you can do some memory acquisition on your own systems. Just fire up a virtual machine, take a memory image, and run plugins against it and learn how to use this. You may even try to sharpen your teeth on production systems, but of course, in this case, you should ask for permissions first, because that may contain sensitive data. And don't forget, there are more ways and tools than just memory analysis. So we have persistent storage analysis, which Toby will talk about next week. We have a lot of network data analysis, which we'll not be covering here, Wireshark or all the NetFlow analysis tools. We have reverse engineering tools like Ghidra or Radar2, which are a quite extensive field and can't cover that here because I'm not an expert in this field. We have seen some everyday tool against obfuscation like CyberChef, or even very simple one tools like strings or object dump or file may come in handy and doing some first step analysis. So just try out some of them. And it sometimes gives the impression that with ever more techniques for rootkits coming up, that the situation is a kind of hopeless, but quoting a old movie, the situation is hopeless but not serious. As it is for every attack and for every way rootkit authors can hide, there's also a way of uncovering their tracks. Unfortunately, for all the defenses we may put up, there's also an attack against this. But this is kind of an ever ongoing race between intruders and defenders, and we will move on over time. But there will always be traces that the adversary forgot or couldn't avoid or did not care about. So my final words before taking questions is seek and ye shall find. So with that, I end my presentation and I'm ready to take some questions.
Thank you very much, Klaus. It reminds me of an episode of Sherlock Holmes I watched that said that everybody leaves some kind of evidence behind them, no matter where they go or what they do. And I think this is key in everything that we do, and particularly online. There's no way of effectively totally 100% hiding. So,
as every police officer will tell you, there aren't
indeed
any perfect crimes.
Indeed.
At least not traceless perfect ones.
Indeed, absolutely.
So there's
Great.
a mentioning of a reverse engineering tool, Cutter, which is
Yes.
something I haven't heard about yet, but okay, we'll give it a look.
Okay. Fantastic, fantastic. If you have individual tools that you find useful, then I think if you speak to the team, drop emails to Klaus or Christine, I'm sure that they'll be able to take a look and maybe include them in the wikis or whatever as a group support, because obviously there are support groups for hackers. It's always good to have support groups for unhackers, if that's a phrase. Cool.
Yeah, for example, if you're going to look for rootkits, just do a search on GitHub for rootkit, and you will get swamped with a couple of 100 entries. But if you just want to get some samples of malicious code to work with and compile yourself and modify yourself, yeah, you will find plenty of examples for this. Some of it's quite outdated, but the Bedevil one I found just before I was preparing this presentation.
Fantastic. Okay, well, I don't think we have any other questions, so we'll call it a day there. Thank you so much, everybody, for turning up. We'll, as I say, we've got this recorded, so the recording will be available as soon as we can get it processed and uploaded and sorted out. So thank you all, and there isn't one next week. Is that correct, Sarah? It's in 2 weeks' time.
Yes, that's correct. Nothing next week, but 2 weeks' time. So we look forward to seeing you there. And if you do have any questions in advance, feel free to submit them.
Okay, that's on the 25th, so that's the Wednesday.
Yeah.
So yeah, absolutely. Just to put a date in your diaries for everybody. Thank you, and see you in 2 weeks' time. So, thanks a lot.
Thanks
Thank you,
from my
Klaus.
side, and have a nice time, and thank you for watching.
Thank you all.